All right, welcome to the Chapter 3 Part 2 video. In this video, we're going to be looking a little bit deeper at exponential functions and introducing logistic functions, and we're going to introduce and explore exponential and logistic functions through modeling. So looking at examples of when we would use these types of equations. So the first thing that we're going to look at is looking at percentage rate of exponential functions. So we started looking at this last class, but looking at that model again, the formula that we looked at the end of the last video. Then we're going to look at exponential growth and decay models, look at using a regression model. So we've seen linear regressions before. We're going to look at now an exponential regression. And then we're going to look at logistic functions and look at a model of a logistic function. So you already explored logistic function through the activity that we did in class, but this will give you a more solid application for a logistic function. Why do we care? Exponential functions model many types of unrestricted growth. That's a key word, is unrestricted, where logistic functions model restricted growth, including the spread of disease and the spread of rumors and many populations. So starting out, we have an example, picking up where we left off in the last video, where we had our population formula for an exponential function. Now, our population, P of t, was written in terms of our initial population, and that was P naught. That was our initial or starting population. Then we had 1 plus R, where R was our rate. If R is greater than 0 or positive, then this is growth. And that makes 1 plus R to be greater than 1. And then if our rate is less than 0, this is decay. And that puts 1 plus R between 0 and 1, right? So we looked at that as a couple different ways of looking at growth and decay. So in this example, what we want to do is we want to take our initial value of 10, that's P naught, and it's increasing at a rate of 5% per year. So our rate is 5% or 0.05. So we have our formula, substitute in our P naught and our rate, and we're left with our population at any time t equals 10 times 1.05 times t. Now, because this is 5% per year, t is time in years. And that means if t equals 6 months, then I would have to convert it to 0.5 years. Okay, so we have to look at our rate to give us what time frame t is referring to. So if t is in months, then that's going to be different than if t is in years. Okay, so let's look at an example where we apply this. In this example, we're modeling bacteria growth. So we start out with a culture of 200 bacteria. So I have 200 bacteria in a petri dish. It doubles every hour, and we want to know when will the number of bacteria equal 350,000, and we're going to round to the nearest hour. So my initial population is 200. Doubling every hour, well, if it doubles, if I have 5 and I double it, then I have to add another 5. So I take my initial 5 and I add the whole value back. So doubling is increasing by 100%. I'm doubling it, then I'm taking that initial, whatever initial value it is, and I'm adding that whole value back. So I'm increasing it by 100%. And that means our rate is 1.00 or 1. And then we want to know when the bacteria will be 350,000. So that's P of t. That's the population after a certain amount of time, and we want to know what the time will be. So if we substitute this into our formula, P of t equals P naught times 1 plus R to the t. So we have 350,000 equals 200 times 1 plus 1 to the t. Divide both sides by 200. 2 goes into 3, 1. 2 goes into 15 7 times. 2 goes into 10 5 times. Cross out the 2 zeros. I'm left with 1 0 left, equals 200, cancels out. Okay, so now I want to know what power of 2 is closest to 1750. So I want to know my powers of 2. So if 2 to the first is 2, 2 squared is 4, 2 cubed, 4 times 2 is 8, 2 to the fourth, 8 doubled is 16, 2 to the fifth, 16 doubled is 32, 2 to the sixth is 64, 2 to the seventh is 128, 2 to the eighth is 256, 2 to the ninth is 512. Yep, 2 to the 10th is 1024. 2 to the 11th is 2048. And now I have passed 1750. Okay, now exponential functions are a little bit tricky for how we would round. It's not exactly halfway between, but 1750 is definitely closer to 2048. So in this example, because we haven't gone over logarithms yet, in this example, rounding based on 1750 being closer to 2048 than 1024 is okay. But just know, if we remember the shape of an exponential function, 1024, 1750, and 2048 might not be evenly spaced. It's not a linear function, okay? So we're gonna say this is approximately 2 to the 11th, 2 to the 10 point something, right? So that means that t is approximately 11 years, not years, hours. Okay, now by the end of this chapter, you will know how to find t to the exact value, but since we haven't reviewed logarithms together, you won't need that for this section. Okay, let's take a look at our next example. And for this example, we're going to need to recall scatter plots. Now, we did scatter plots in chapter 1, and we did linear scatter plots. So we looked at when we plotted some data and it looked like a line, and then we found the equation that would go through those points as a line closest to the points. Okay, but now what we're going to do is we're going to look at this as if it's an exponential function. Okay, so we want to look at 1890 as our starting time. So we're going to make a column here for X, and X will be the number of years since 1890. So in 1890, it has been 0 years since 1890, 10 years later, 20 years later, and so on. So really what we're doing is we're subtracting 1890 from each year. 30, 40, 50, these are just going up by 10, so not too bad. And as a reminder, this is, if I take 1980 minus 1890, I should get 90. And that is what I get, okay? In order to calculate these, to calculate the regression, what I wanna do is put these into my calculator as list 1 and list 2. So I'm gonna remind you how to do that. I'm gonna pull up my calculator here. So the first step is to get into the lists to tell the calculator the data. So I'm gonna go into Stat, enter for edit. Now I already have the data typed in, but for example, if I had something typed into my list that I wanted not to have anymore, what I can do is go up to the list name, hit clear and enter. That will clear out the list. If I just hit clear, it won't clear out the list. I have to hit clear, enter. Okay, now you don't want to hit delete. If you hit delete, then you have to restore your settings. Okay, and I can go through that with you. If you hit delete by accident and you want to restore it, I can go through that with you. Okay, so if you don't have L1 and L2, send me an email. I'll send you back a tutorial on how to restore those lists. But essentially, once you type in list 1, those are your X values. List 2, those are your populations. Go ahead and pause the video if you need a little bit more time to type those in. What we want to do now is calculate that regression. So in order to do that, we need to know what this looks like. So to look at this, remember L1 is my X values. I'm going to create a window. And I want the window to see all of my X values. So my X values go between 0 and 90. So I'm going to make my window go from 0 to 100. That means I'm going to have a point right on the edge of my window somewhere. Okay. Normally, what I would do is I would go a little bit further. So I might go from -10 to 100. Okay. Actually, I will do that. That way we can see all of the points clearly. So we'll go from -10 to 100. Now my Y values, my smallest Y value is 62.9. My biggest Y value is 226. So I'm going to choose Y values. I'll go from 50 to 250. Now, if you go 0 to 300, that's absolutely fine. But you want to pick a value that is less than 62.9 and more than 20 or 226.5. And then what we're going to do is we're going to go into our window, and you'll see I already like kind of tested this out, but I'm going to go from negative to 100. From -10 to 100. Make sure when you're typing this in, you're not doing -10. It has to be a -10. And then, so my X minimum is -10. My X maximum is 100. We'll change my Y minimum, we'll say is 50, and my Y maximum to 250. Okay, and then the last step, in order to tell the calculator, I don't just want to graph a function or anything, I want to graph the data that I put in. We have to go into our Y equals menu and turn plot 1 on, go up to plot 1 and hit enter. And that will tell the calculator graph my scatter plot. So now when we hit graph, we fixed the window, we told the calculator to graph my scatter plot, graph the lists. So now we should have these points. Okay, now I recognize that that could look like a linear equation, right? But I'm telling you that we're going to do, instead of a linear equation, I would like us to find the exponential function. So in order to do that, just like finding the linear equation, we're going to go back into the stat menu. But now when we go over to calculate, instead of using option 4 to make a line, we're going to go all the way down to exponential, exponential regression. So that should be option 0. We're going to hit enter. And then just like before with the line, we're going to use list 1 and list 2, but we also want to store this as a Y equals. So we're going to go into the vars, over to Y vars, function, Y1, enter. And then one more time, enter to calculate. And that will give us our exponential regression. So that tells us that my function is 66.993 times 1.014 to the X, if that's rounding to 3 decimal places, okay? So we plotted the points using 1890 as time 0. We set the viewing window. We set the viewing window based on our values of X and Y. We chose the appropriate regression. I told you to choose exponential. Then we calculated and stored the equation. So since we stored the equation, when I go into Y equals, I should see the equation here now. And when I graph it, I should be able to see the function. Okay. So the second part of this problem is actually using this function to predict something. So now what I'd like to do is use this population data to predict the population in the year 2000, okay? Now our actual population in 2000 was approximately 281 million. That's for the US population. So what I wanna do is see how far off we are. So we're going to go into our table now. Now, if I go into the table, usually it starts at 0, 1, 2, maybe -1, -2, depending on where you were looking. But I don't want to start at 0. I want to know in the year 2000, what will my X value be? So we're going to go second quit to get back to our main screen. And we're going to say in the year 2000 minus 1890, because that was the year that we started at. We have been 110 years since 1890. And that means in order to find my predicted population, I want to know what the Y value is when X is 110. Now we can plug it into our approximate equation, but the most accurate information that we're going to get, the most accurate answer is from our table. but we don't want to start at 0 and have to press down 110 times. So what we can do is, just like changing the window for the graph, we can change the window for the table. So hit second, table setup, and you want your table to start at 110. That way, when you go second table, that shows you your XY table, it already started at 110. We don't have to hit the down arrow 110 times. And so we know that when X is 110, Y is predicted to be 308.37. Okay, but our actual population was 281. So 308.37 minus 281 should give us 27.37. Okay, so based on the data, we would expect the population, to be 308.37 million. Actual was about 281 million. So we were off by 27.37 million. Okay. Now, in the grand scheme of things, 27 million is a lot, but it's about 10% of our population. Okay, so it's not a huge amount, but it is larger than we would like our margin of error to be. So what happened is that even though this started out maybe looking exponential, it started flattening out. And that's what happens to a lot of populations, because there aren't enough resources for unrestricted growth. And so the model that we use to look at restricted growth, when there's a ceiling, when there's a maximum, is called the logistic function. So let's take a look at logistic functions. Let me try that again, clearing my screen, all the drawings, there we go. Okay, so when we look at exponential growth, it is unrestricted. We talked about this earlier in this video. Exponential growth is unrestricted, okay? If my growth is restricted, then it has a maximum sustainable population, or a ceiling. And when I have quick growth by a factor it's just growing really fast, it's doubling, it's tripling, it might even be growing by 10 or 20%, which doesn't sound like a lot, but in the long run, that's a lot. And so when it's growing quickly, but it has a ceiling, that is a logistic growth function. So it starts out growing really fast and then it levels off. Now, a logistic function has two horizontal asymptotes. That's what makes it level off. And that top horizontal asymptote is the ceiling. So for a logistic function, we have A, B, C, and K. We have two different ways of writing our logistic function. Our base has to be less than 1. And our logistic growth function is a function in terms of x. So notice here, this is an exponential function and this is an exponential function. So we have a number divided by 1 plus an exponential function. And as long as the base is smaller than 1, that is a logistic function. Okay, so if my exponential function has a base that is less than 1, that is a logistic function. Now, you might be saying, well, but e is approximately 2.7. Yes, but it's e to the negative power, and k is positive. So that means it's 1 over 2.7 really as the base times k, or to the kx. And 1 over 2.7, which is about a third, is definitely less than 1. Okay. And that numerator, that number in the numerator, that is the limit to growth, or the ceiling. Or we can also call it the maximum sustainable population. Okay, now you had a chance to play with logistic functions a little bit, but let's look at an application to these. And we're going to look at the application of a rumor spreading. So let's suppose that we have a high school and we're only observing the high school. We're not observing any people outside of the high school population. So the high school has 1,500 students, and there's 5 students who decide to start a rumor, and it spreads with this logistic function. Now, 1,500 divided by 1 plus 29 times e to the negative 0.9 to the t. Okay, so because it's e to the negative 0.9 t, that has that base, right? Because that exponent within our exponential function is negative, that's what makes the base about 1/3. Okay, and that models the number of students who have heard the rumor by, this is a typo, there shouldn't be a period there, which makes this a lowercase t, by the end of t days, where t equals 0 is the day the rumor begins to spread. So the day that these 5 students go to school and start spreading the rumor, that is day 0. Okay, how many students have heard the rumor by the end of day 0? Well, our function models the number of students who have heard the rumor by the end of the day. So the end of day 0, we are looking at S of 0. Now S of 0, not too bad to calculate. I have 1,500 divided by 1 plus 29 times e to the negative 0.9 times 0. Well, that's going to make my exponent 0, and anything to the 0 is 1. So that becomes 1,500 divided by 1 plus 29, which is 1,500 divided by 30, reduced by 10, and then reduced by 3. Whoops. There we go. Reduced by 3 is 50. So that's 50 students by the end of day 0. We want to know then, how long does it take for 1,000 students to hear the rumor? So we want S of t to equal 1,000. Well, we know that S of 0 equals 50, and we are going to solve this very similarly to our previous example, where we're going to use our calculator. Whoop, where did my calculator go? Okay, and what we're going to do with our calculator is we're going to put our equation, and since t is the only thing that's changing, that's the only part of our equation that's going to change. So we have 1,500 divided by parentheses 1 plus 29 times e to the, so if we do second, next to 4 is the natural log. It has a little e to the x next to it. So e raised to the negative, not minus, negative 0.9 times, and this is where we're going to put our t value. So we already found what happens on day 0. We want to know what happens now on day 1. Enter. That tells me that at the end of the next day, so not the day the rumor started, but the first day after the rumor started, there are 117.3, so 117 students who know the rumor. Okay, now I want to do that same calculation, but I want to change the last number. I don't have to retype the whole thing. So here's a shortcut. If I want to retype the last entry, I can do second, enter. And that will retype the last thing you typed in. If I did it again, it would type the second to last thing that I typed in. But I'm going to go right, right, right. Sorry, that was left, 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 and change my 1 to a 2. And then I hit enter, and that tells me at the end of the second day after the rumor has started, there are 258.9. So that's 259 students who know the rumor. Then I'm going to do the same thing. So second, enter, left, 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 3. So the third day after the rumor has started, S of 3, there are 508.6. So that's 509 students who know the rumor. Then I do second, enter. So we're getting closer. We're about halfway there. On the fourth day after the rumor, now we're up to 800. 836.8 or 9. Anyway, that would be 837 people because I can't have part of a person. Okay, and then second enter. Change the 4 to a 5. Now we have passed it. So S of 5 equals 1134.5. So somewhere between 4 and 5. So on the fourth day, and I'm going to move my calculator here, about halfway through the day, not in the morning, because in the morning of the fourth day after the rumor spread. So this is the day the rumor started, first day, second day, third day, fourth day. No, it's on the fifth day, Because at the end of the fourth day after the rumor has started, there are 800 people who know. So on the fifth day, about halfway through the day, 1,000 students know. That's on day 4.5. It's about 4.5, okay? Halfway between day 4 and 5, if we're looking at these as day 4 and day 5. But really, at the end of day 4, not enough people know. It's halfway through the fifth day that 1,000 students will have heard the rumor. Okay, now again, in order to solve for t exactly, we need to review logarithms. So by the end of the chapter, we'll be able to solve that exactly and get an exact answer for t. But for now, because we haven't reviewed logarithms yet, using this kind of substitution test and then approximating, that's going to be sufficient. Okay, if you have questions, send me an email. Otherwise, I will see you in class to work on some practice for this.